Sequences and series. You're probably aware of them. A sequence is just a collection of numbers. They can be well defined with a pattern, like this one, or they can be completely random. Some sequences might even just go on forever, without end. A series, on the other hand, is simply the sum of all the elements in a sequence. In this video, however, I want to dive deeper and explore recursive sequences, specifically linear recurrences and their generating functions. Don't worry if the last two sound a bit abstract to you, they'll be covered in detail. However, this part will be dedicated towards linear recurrences. I'll make a part 2 dedicated towards generating functions. Let's briefly introduce recursive sequences. A recursive sequence is a sequence of numbers in which each term is defined based on previous ones. So for example, the terms in this sequence are always 2 more than the previous one. Now, to activate a sequence, we need to define a starting term. So we can have, for example, a1 is equal to 1. And this becomes a neat way to compute the first few terms in the sequence. Just plug it in repeatedly and you get our answer. However, what about something like A50? Well, this sequence is actually simple enough to find a pattern, but it's not like all sequences will be simple as this one. So we kind of need a definite way to find a formula for an that doesn't involve repeated computation. Consider this. Move an minus 1 onto the other side. If we write the same recurrence a bunch of times, except we shift the index down by 1 the closer we fall to the ground, if we add up all of these equations, notice that all the intermediary terms cancel out, and all we're left with is an minus a1 is equal to 2 times n minus 1, since 2 is added n minus 1 times. Now, recalling that a1 is equal to 1, we can move 1 over onto the other side and simplify to get our formula. Plug in n is equal to 50 and we get our answer. That wasn't bad. However, what if the terms were defined by 2 previous ones? We'll start by looking at one of the most famous sequence of numbers in history. This over here is the Fibonacci sequence. It satisfies f1 equals to 1, f2 equals to 1, and fn is just the sum of the previous 2 terms. Take a look at the sequence. It really does satisfy the recurrence. Now, you might wonder, is there a formula for fn? Can we maybe compute f200 with it without using repeated calculations? We might want to start by graphing the Fibonacci numbers and observing their behavior. And when we do, we see that they grow almost like in an exponential curve. So we suspect that they might satisfy some sort of exponential function, call it c to the n for some constant c. Then we can replace this into our formula and divide both sides by c to the n minus 2. This yields a quadratic, which we can solve with the quadratic formula, which will give us 2 distinct roots. We might think that we just plug in c and we get our formula, but we quickly realize that this doesn't even satisfy the first term, so what happened? The truth is, the formula is actually a linear combination of the roots to some power. Now, you might be wondering, how did you even get this? That's not important. We're only here to just demonstrate how this is true. So, we know that c to the n is equal to c to the n minus 1 plus c to the n minus 2. If we distribute the lambdas in and rearrange a bit, we see that fn minus 1 and fn minus 2 are nested within this equation. So, we verified that the recurrence is indeed satisfied. Knowing that this is the correct form, we will proceed. If we plug in 1 for n, we get an equation. We know what f1 is, it's just 1, and c1 and c2 were the roots. So substituting in their values and simplifying, we get 1 equation. We can similarly get another one if we plug in 2 for n. Now, this doesn't look that inviting, even though we could solve, but we could also first get f0 by the original recursion. This helps us produce a simpler equation because the coefficients will become 1 by the exponent. Now we can solve for lambda 1 and lambda 2. We can finally substitute the lambdas back into the equation. along with some factorization and rearranging, and we got our formula. I encourage you to try it for like n equals to 1, 2, 3. It actually works, but something like f200 is still rendered impractical because of the calculations shown here. You can still use your calculator or computer though. And by the way, this is called Binet's formula because it was derived from the French mathematician Jacques Binet. Also, this might look like a weird formula for positive integers, but try to think of a reason why it actually works. Obviously, it should work because of the way that we derived it, but can you think of a reason from a computational standpoint why the outcome should always be an integer? This method actually works in general. Let's take a random recurrence, this one. We wish to find a closed formula for an. Let an equals to c to the n. Then we can get a new equation, and when we divide both sides by c to the n minus 2, we have a quadratic in which we can get the roots. Next, we write the solution as a linear combination of the roots to some power, and then we can form two equations by plugging in n equals to 1 and 0. Solving for lambda 1 and lambda 2 allows us to plug this back into the original solution to get our formula. So if I gave you a random recurrence like this, I'm sure you're able to get the closed formula. Try it. Are you back? Did you see the issue? Let an equals to c to the n. Then we get another equation and a quadratic. Now, we realize there's no real roots. So is there no formula? Let's ignore this, though to proceed, we'll need to use complex numbers. Now from here, we can get two equations from the linear combination, and we can solve for lambda 1 and lambda 2. Plugging them back into the original form actually yields the formula. Believe it or not, this actually works. It will produce real numbers, integers in fact, from the sequence. As a reminder, here was the original recurrence. Compute the first few terms using the recursive formula, and then with the formula we derived. Thank you for making it to the end of this video. Stay tuned for the video about generating functions. And also, if you made it this far, check the comments.